In this video, we're going to conclude our discussion of ordinary differential equations. In particular, we're going to talk about solution methods for boundary value problems, or BVPs. So from the previous sections, we saw that initial value problems have all of the conditions specified at the same value of the independent variable. So for example, the dynamic system represented by the ordinary differential equation m d2x by dt squared plus c dx dt plus kx equals 0 usually has the initial position x0 and velocity x prime of 0 specified at the initial time t0. So the important thing is that both of these are specified at the same value of the independent variable, t0. In contrast, boundary value problems, or BVPs, are ordinary differential equations whose boundary conditions are given at different values of the independent variable. So usually these points are the extreme points of the region of interest or the boundaries of the domain. And because we need to have the boundary conditions given at least two different values of our independent variable, this requires that to have a boundary value problem, we must have at least a second order ODE. So let's consider a boundary value problem with y as the dependent variable and x as the independent variable. The boundary conditions would be given in terms of y, or the derivatives of y, at different values of the independent variable x. And there are two main types of boundary conditions. So the Dirichlet boundary conditions are boundary conditions that are given in terms of the variable y itself. And the Newman boundary conditions are where the boundary conditions are given in terms of the derivatives of y. So there are various methods to solve boundary value problems. Some of the most common ones are the shooting method, the weak formulation method, or the finite difference method. In the shooting method, the boundary value problem is solved as an initial value problem, and the initial conditions are varied until the boundary conditions at the extreme ends are satisfied. So if we have this boundary value problem, d2y by dx squared is equal to some function of x, with boundary conditions y at 0 is equal to y0, and y at L is equal to YL. We can convert this system into an initial value problem with the boundary conditions y of 0 is equal to y0, and then the derivative of y at 0, or y prime of 0, is equal to some variable s. And then we can use the methods for solving initial value problems to find the solution across the entire domain. And then after the solution is obtained, the value of y of L is compared with the specified value YL, and then S is varied until those two match. So basically until our y at L is equal to the specified value of YL. So we have our system, our boundary value problem with our boundary conditions given at the ends of the domain. So y of 0 and y of L. We can convert this to initial value problem where our boundary conditions are now given both at x is equal to 0. So here we've kept our one boundary condition y of 0, and we've converted the other one to specify the derivative of y at 0, and we say that this is some value s. Then we can use our IVP solution methods to find our solution across the whole domain, and we end up getting some value at the end at y of L. Then we vary this value s until y of L matches our specified value YL. The weak formulation method relies on converting the problem into a different integral form and finding the best solution that would satisfy the new form. Examples of these types of methods are in the finite element analysis method or the weighted residuals method. The finite difference method relies on approximating the boundary value problem with difference equations by replacing the derivatives of the function with their finite difference approximations. So basically the approximations that we talked about in chapter 10. And the finite difference method is the only one that we will study in detail in this course. The other two methods as well as any other BVP methods, are not covered in detail in this course. So let's go through the details of the finite difference method, and we'll see how it can be implemented in a few different examples. So first, let's consider a boundary value problem with the dependent variable y and the independent variable x, where x is on the domain from a to b. The finite difference method in a boundary value problem relies on discretizing the domain from a to b into n intervals, with a is equal to x0, and then up to increasing values of x, up to xn is equal to b. And we assume a constant step size h is equal to xi plus 1 minus xi. The values of the dependent variable at the interval junctions are denoted similarly, so y0, y1, y2, up to yn. So if we've got this, this function in our domain here, we discretize the domain into n intervals with our x's defined at each interval. Constant step size h is equal to xi plus 1 minus xi. The corresponding y values are defined, are denoted similarly, as you can see here. So the finite difference method seeks to find a numerical solution to each yi by solving difference equations, which are formed by replacing the derivatives in the boundary value problem with finite difference approximation scheme. And it's usually the centered finite difference scheme, which we talked about in chapter 10. And we typically use the basic version of the centered finite difference scheme. The Dirichlet boundary conditions can be directly imposed on the known values of yi. And the Newman boundary conditions can be imposed as additional difference equations using an appropriate finite difference scheme, depending on the order of the derivatives. So let's look at, we're going to look at 4 examples to demonstrate how to use the finite difference method to solve various problems. So the first example is going to be solving the heat equation. So the differential equation describing thermal energy within objects, which is the steady state heat equation, is an example of a boundary value problem that can be solved using the finite difference method. And you can take a look at the online notes to see a derivation of the differential equation for this particular problem. So let's consider a one-dimensional rod of length 10 meters connecting 2 heat sources of constant temperature. So on one side, the temperature is equal to 40 degrees, and on the other side, the temperature is equal to 200 degrees. And so both of those temperatures are kept constant. And then the ambient temperature around the rod is equal to 20 degrees. And we want to find the temperature variation within the rod at steady state. So the steady state heat equation can be derived by balancing the amount of heat energy per unit time entering and exiting through the control length of the rod. And the resulting equation is shown here. So d2t, where t is temperature, by dx squared is equal to 1 over 10 times t of x minus 20. So this temperature is a function of x, where x varies, x equals 0 at the left end of the rod and x equals 10 at the right end of the rod. And the outside ambient temperature was 20 degrees. So this is our boundary value problem, and then the Dirichlet boundary conditions specify the temperature at the ends, x is equal to 0 and x is equal to 10. So t of 0 is equal to 40 and t of 10 is equal to 200. So we want to use the finite difference method with 4 intervals to find a numerical solution to this boundary value problem. So the exact solution to this differential equation is given as shown here. And it's important to note that an exact solution is not always available, but in this case, one is. So we can compare our solution to our exact solution. So the numerical solution is obtained by first discretizing the domain into 4 intervals, with h is equal to the total length of our domain 10 divided by the number of intervals 4, which is equal to 2.5. So you can see the values of x here are 0, 2.5, 5, 7.5, and 10. Our boundary conditions at t equals 0, we've got 40. T equals 4, we have 200. And then the temperatures at the internal points are unknown. So the given boundary conditions are this Dirichlet type, so T0 is equal to 40 and T4 is equal to 200. The remaining three unknowns can be obtained by using the basic formulas of the centered finite difference scheme to replace the derivatives in the differential equation. The centered finite difference for the second derivative is given as the expression shown here. So d2t by dx squared for xi is equal to ti plus 1 minus 2ti plus ti minus 1 divided by h squared. And you can take a look at chapter 10 to see the where this equation came from. So for this problem, this is our differential equation shown here. So we're just going to use the centered finite difference approximation in replace of this second derivative at each value of xi. So this can be used to write three equations of the form shown here. So ti plus 1 minus 2ti plus ti minus 1 divided by h squared is equal to everything on the right hand side here. So 1 over 10 ti minus 20. So this results in the following three equations where, again, we've put in our boundary conditions. T0 is equal to 40, T4 is equal to 200, and we're using the step size h is 2.5. So when I is equal to 1, we get this equation. When I is equal to 2, we get this equation. And when I is equal to 3, we get this equation. Then we can simplify and rearrange these equations into a linear system of equations, which we can write in matrix form shown here, to solve for our unknown values, which are the temperatures at the points 1, 2, and 3. So solving this, we find that T1, T2, and T3 are given by these values shown here. And then we can combine this with our T0 and our T200 to get the full numerical solution and draw a plot of both the numerical solution shown in the black dots overlaid with the exact solution, which is shown in the blue curve. And you can see that even with the pretty big spacing for this problem, that the numerical solution is almost identical to the exact solution. So let's repeat this problem with, instead of using Dirichlet boundary conditions at both sides, we're going to have one at the left side, so T0 is still equal to 40, and a Newman boundary condition at the other end. So instead of specifying the temperature directly, we're going to say that the derivative of the temperature, so dt by dx, at x equals 10 is equal to negative 3. So this is how we can now discretize our domain. So we're again using h is equal to 2.5. So we've got our Dirichlet boundary condition specified here. T0 is equal to 40. But on the right-hand side, we're not specifying T4 exactly. We're specifying the rate dt by dx at x is equal to 4, which is equal to minus 3. And again, we can find the exact solution, which in this case is given as shown here. So the numerical solution is obtained by discretizing the domain into 4 intervals. The boundary condition on the left-hand side is set T0 is equal to 40. And the remaining 4 unknowns in this case can be obtained using 4 equations. So the first 3 equations are composed in the same way that we did in the previously, where we use the basic formulas of the centered finite difference scheme to replace the derivatives in the differential equation at the 3 intermediate points. And then the last equation is composed by using the backward finite difference scheme at x equals 4, or x4, and equating it to the Newman boundary condition. So the 3 different equations at the intermediate points have the form shown here. So same as in the previous problem, where we're using this centered finite difference for the second derivative to replace the second derivative in our differential equation, which results in these 3 equations. So for when I is equal to 1, I is equal to 2, and I is equal to 3. And then the last equation is obtained by using the backward finite difference at x4. So this is just the backward finite difference for the first derivative. And then we set this equal to minus 3 because we said that our boundary condition was that dt by dx at x4 is equal to minus 3. So we're replacing this using the backward finite difference approximation. So this gives us 4 equations in our 4 unknowns, which are the temperatures at T1, T2, T3, and T4. And so we can solve this linear system of equations to find the temperatures at each of those points. And we can combine this with the prescribed boundary condition at T0 to plot the numerical solution, which is again the black dots, and the exact solution, which is the blue curve. And using this example, this demonstrates that the numerical solution of the same differential equation with Newman boundary conditions tends to provide a less accurate result than when only Dirichlet boundary conditions are used. So you can see that we start to see some deviation from the exact solution here. The numerical solution improves and approaches the exact solution as the number of intervals is increased. So this shows the difference with 4 intervals versus 18 intervals. And you can see here we're starting to get a pretty good estimate for the majority of the domain, and it's starting to deviate a little bit at the end of the domain. So let's take a look at another example. So here we have a second order boundary value problem with boundary conditions at 0 is equal to 1.5 and u at 3 is equal to 2.5. We want to use the finite difference method to find a numerical solution using n is equal to 5 intervals, and then compare with the exact solution, which is given as shown here. So we're going to discretize our domain into 5 intervals, so our h is equal to 0.6. So this leads to these values of x, and the values of u at all of the points are denoted u0, u1, u2, up to u5. And the boundary conditions in this case are both the Dirichlet type, with u0 is equal to 1.5 and u5 is equal to 2.5. So the remaining 4 unknowns, which would be these values, are obtained using the basic formulas for the centered finite difference scheme to replace the derivatives in the differential equation. So this is our differential equation this time. So we've got the second derivative of u plus the first derivative of u plus u is equal to 1. So here we can use the centered finite difference for the second derivative and the first derivative, and then we just have our u at I. So we can write this this form of equation at each of the intermediate points, and we get these 4 equations, which we can write as a linear system of equations with 4 equations and 4 unknowns. And we can solve this linear system of equations to give us the values of u at u1, u2, u3, and u4. Then we can combine this with u0 and u5 to draw a plot of the numerical solution, which are the black dots, as well as the exact solution, which is the blue line for this problem. You can see that the maximum error in this numerical solution is obtained at x is equal to 1.2, which is this one here. At this location, the exact solution is equal to 7.6803, while the numerical solution is 9.1183. So this gives a relative error of about minus 19%. And we can, so the accuracy of the solution depends on the accuracy of the finite difference scheme used. And we know that the finite difference scheme's accuracy, of course, is related to the step size h, so we can decrease the value of h to improve our numerical solution. So here, comparing n is equal to 5 versus n is equal to 20, you can see that we get a much better approximation using a higher number of points or smaller intervals. So let's look at another example. Here we're using the differential equation to describe the displacement of a hanging chain as a function of the weight per unit length W and the desired horizontal tension in the chain, which is T0. So the differential equation is given as shown here. So it's a second order nonlinear differential equation. Y is the dependent variable, which is the chain curve, and x is the independent variable, which is the horizontal distance along the chain. So we're modeling something that looks like this, where our x kind of goes along here, and y is this vertical height of the chain. And the solution to this equation is called the catenary, and you can take a look at the some articles to understand a little bit more about this equation. So this is our differential equation, and if we assume boundary conditions at y of 0 is equal to 0 and y of 4 is equal to 0, with a weight of 1 and a tension of also 1 unit. We want to use the finite difference method to find a numerical solution by dividing our domain from 0 to 4 into 5 intervals. And then we can compare with our exact solution, which is given as shown here. So we can notice that this equation is a nonlinear second order ODE. So the numerical solution is obtained by discretizing the domain into 5 intervals. So here our h is equal to 0.8, and we've got our 2 prescribed boundary conditions, y is 0 is equal to 0 and y of 5 is also equal to 0. And the boundary conditions are the Dirichlet type, so we can prescribe the values of y exactly. The remaining 4 unknowns are the y's at all of the positions at all of the points in between can be obtained by using the basic formulas of the centered finite difference scheme to replace the derivatives in the differential equation. So we've got our differential equation and we know the centered finite difference scheme, so we can write 4 nonlinear equations of the form shown here. So where the second derivative is replaced with the centered finite difference, and here the first derivative is also replaced with the centered finite difference. So this results in 4 equations as shown here. So we're again putting in directly the boundary conditions. They appear directly in the equations, and h is 0.8. And you can see that the resulting equations are nonlinear because the differential equation itself was nonlinear. So because we have a nonlinear system of equations, we can use a solution method such as the Newton-Raphson method with some initial guesses such as minus 0.1 for all of the unknowns to yield the solution of the position at y1, y2, y3, and y4. So combined with our endpoints, y0 is equal to 0 and y5 equals 0, we can draw the plot showing the obtained numerical solution in the black dots and the exact solution in the blue curve. And you can see that with this, even with this fairly large step size, the 2 solutions are quite close to each other. And again, we can decrease the value of h to get a numerical solution that is closer to the exact solution, so improve our estimate, as you can see here. So we'll look at one more example, looking at this boundary value problem here. So we've got 7 d2y by dx squared minus 2 dy dx minus y plus x equals 0. Boundary conditions, again, of the Dirichlet type, y of 0 equals 5 and y of 20 is equal to 8. With an h of 2, we want to use the finite difference method to find a numerical solution on the domain from 0 to 20 and compare with our exact solution, which is given here. So again, the numerical solution is obtained by discretizing the domain into 10 intervals. So here h is equal to 2. So all of our values of x we can write down here. And the boundary conditions are given as the Dirichlet type. So we know that y0 is equal to 5 and y10 is equal to 8. The remaining 9 unknowns are obtained by using the basic formulas of the centered finite difference scheme to replace the derivatives in the differential equation. So this can be used to write 9 equations of the form shown here. So we're replacing our second derivative as well as our first derivative, and then we've got our y as well as our x for each I. So writing this with each I from 1 to 9 at all the intermediate points, and prescribing the boundary conditions directly in the equations, we end up with these 9 equations for our 9 unknown variables. So this results in a linear system of equations that we can write in matrix form as shown here, and this can be solved very easily to find our solution for y1 through y9, which is given here. So combining this with y0 is equal to 5 and y10 is equal to 8, we can draw the plot of the numerical solution, or the black dots, and the exact solution shown by the blue curve, and we get an excellent approximation of the solution with this step size. So this concludes the section on methods for solving boundary value problems, and it concludes our chapter of ordinary differential equations.